So the idea that I'm going to present is pretty elaborate. It's been around since the 90s, and I think it's cool, but it hasn't been used much. It's just from a theoretical point of view, I think it's an interesting idea. There are many applications in min law problems as well, but the very first application was on mixed integer linear optimization problems. So I hope I got all the indices and numbers right, but in general, so X is a feasible set of a mixed integer linear optimization problem. X variables that are binary, so unfortunately in this publication they flip the meaning, so X is binary and Y is continuous. Both variables are between 0 and 1, and the feasible set is also described by a set of linear constraints. So just remember that X is the binary variable here, and there are n such binary variable and I think P variables Y between 0 and 1. So this sounds, I mean, every time I read it, less and less now, but every time I read the technique, it sounds to me a bit bonkers. For one reason, you're taking a nice, well-defined linear optimization problem, and you're making it nonlinear and non-convex. So the method consists in doing the following. Clearly, the first part is the part that creates a problem that is going to be non-convex, and the first step is exactly this. You take every row, every constraint from the set of linear constraints, and you multiply it by all possible terms that are monomials resulting from the product of a few terms xj and a few terms y minus xj. The reason behind this is that xj and 1 minus xj are all terms that are non-negative because xj has a lower bound of 0 and 1 minus xj has a lower bound of 0 as well because it's bounded from above by 1. So, and you do this for all sets J1 and J2 that are disjoint, and such that the total degree of this monomial, it's not exactly monomial because there's a 1 minus x here, is equal to d. If you ask me why I would do this, I wouldn't know, but this is the method. There are plenty such terms. You would be supposed to take all the m constraints, and for each of them, you rewrite it by taking each of these 2 to the d times, what is it? It's like m, the p over d pretty much. So it's a large number of problems. This is the reformulation part. Sorry, this is, you're setting up a problem in order to be reformulated. The reformulation part comes next. And I think now that I look at it, I think it might be better to write an example. So let's write a small example because that term over there is scary. So we want to minimize x1 plus 2x2 plus y1, subject to 2x1 minus 3x2 plus 4y1 is greater or equal than 5. And then just one more constraint. X1 plus y1 greater or equal than minus 2. X1 and X2, as I said before, are binary. Y1 is between 0 and 1. If we wanted to apply this technique to this thing, then we would have to start with the following. So the first constraint is 2x1 minus 3x2 plus 4y1 minus 5. And we multiply it by a product of that form whose degree is d. So we need to start with the d. Let's say that d is equal to 2. And let's take the first term, which is equal to let's say x1 times 1 minus x2. So this is the first product, and this is the second product. They don't need to be both non-empty. We could easily just add x1 times x2 and nothing else. So for a choice of d equals 2, that is the degree that we choose to multiply by is equal to 2. This is the first constraint, and I have it greater than or equal than 0. I just moved the minus 5 inside. I can do it for a lot of other terms. I could do x1 times x2 times the same, 2x1 minus 3x2 plus 4y1 minus 5 greater or equal than 0. Let's try something with the second constraint. So let's try 1 minus x1 times x2 times the second constraint, which is y1, x1 plus y1 minus 2 is greater or equal than 0. I'm sorry? Yes. Less 2, yes, so plus 2 here. Thank you. This is just the beginning. We need to add a lot more of these terms. So I'll stop here. But what happens now is the following. The next step is, well, next step is not even there yet. We should multiply everything here. What we would get, let's try to write this out completely. We probably need more than one blackboard, but let's try to write the first constraint, which is going to be a long one. So the first term is going to be x1 times 1 times 2x1. So 2x1 squared minus 2x1 cubed, because it's, oops, no, x1 square x2, because it's x1 times minus x2 times 2x1. Please correct me, because I tend to make a lot of mistakes, as you just noticed. Okay, so let's look at this term now. So x1 times minus x1 times 3 times x2. So x1 times 1 times minus 3x2 plus 3x1 x2 squared. So we're not even halfway through and it's already extremely messy. Plus x1 times 1 times 4y1, it's 4x1 y1 minus 4x1 x2 y1. And finally, minus 5x1 plus 5x1 x2 greater, finally, and equal to 0. I didn't do much. I just developed that product. So we would have to do the same with the other 3 constraints. What happens here is that we need to do this with many other terms. But what is important is that now we linearize everything. And we get a constraint here where we substitute all the non-linear terms with a new variable, paying attention to one very crucial point. And one of the authors was down the corridor from my office in Clemson University, told me, you know, the whole thing here is the fact that this is all nice and good, but the crucial point is that the terms x1 squared, because x1 is binary, what is x1 squared equal to? x1. So the whole point becomes taking this into linear form, taking into account the fact that x1 squared, x1 cubed, x1 fourth is going to be simply x1. And that is one of the main reasons why the results that we'll show you later actually happen. So this is going to be minus 2x1 squared, or minus 2x1 times x2. And for this, we need to introduce an extra variable, which we call call it y, 1, 2, minus the same variable 3 times y12 plus x2 is also binary, so x2 squared is equal to x2, so plus 3y12, and then plus 4 times x1 times y1. Here we have to pay attention to the fact that this y variable is continuous, so we can't really use the same name. We can use a different name, and we call it v11 with a comma in between to divide the indices of the binary variables from the indices of the continuous variables y. And then minus 4 times v multiplying 1, 2, comma 1 minus 5x1 plus 5y12 greater or equal to 0. So we went through step 1 and 2 of the linearization step, and what we end up with, we actually eliminate, we discard information that tells us that actually y12 is supposed to be equal to x1 times x2. So this procedure actually says, no, forget about that nonlinearity. What you have now is simply, what you sacrificed is in writing all these terms for a very large number of polynomials and possibly a large number of constraints. Once you wrote that, the crucial point of the reformulation-linearization technique is that you can go from this nonlinear step to a linear inequality by removing, well, relaxing at this point. You're relaxing these nonlinear constraints by introducing extra auxiliary variables. And the crucial bit is this. You clearly lose tightness in introducing auxiliary variables to remove these nonlinear terms. But the crucial point is that you end up with so many constraints, all of which contain these auxiliary variables, that there is a very thick set of connections between all of these constraints because they all use more or less the same variables. Should I continue? Should we write one for another constraint? I think the method is, so the way this is constructed should be clear. That's a multiplication, sorry. How do we write it? Okay, yeah, let's do this. Okay, so this would be x1 times x2 times 2x1. So
the first question is of the form of xj and 1 minus xj.
Right.
The third one is also of that form.
Mm-hmm. Yes, so for the second one, J1 is equal to 1 and 2, and J2 is equal to the empty set. You're fine with an empty set on either side. More questions? So the crucial bit which we would need a lot of chalk to write is the following. Take this set, the set that you obtain by rewriting all of these constraints as linear constraints, and take the projection. So in other words, take all of these linear constraints, all of them, and project out all the new variables, the y12, the v11, etc. Project them out. So you have a set of linear constraints. You need to project out all these auxiliary variables. What you get is a relaxation of the convex hull of your original set. This is extremely powerful. This is beautiful in a very strange way. And the strange thing is that the tightness of the relaxation you get after projecting out everything depends on the degree with which you create all of these product terms. The higher the degree, so the higher this, see, I keep forgetting. The higher this number, the higher D, obviously, the higher this number. But that simply means that for a very high degree, you're going to get, once you project out all those variables, and it's non-trivial, then you will get a a relaxation of the convex hull of the original set X that is tighter and tighter. In fact, these sets all form a hierarchy. It's called the Sheralian-Adams hierarchy, precisely because it's based on that reformulation-linearization technique by Sheralian-Adams. And you can, so this initial set is the set where you don't actually do anything. You just leave the set as is. As soon as you start multiplying all constraints by terms of degree 1, so x1 or x2 or 1 minus x1 or 1 minus x2, you get this second set after you project out all of these auxiliary variables that is going to be tighter than the initial one. And if you increase the degree, you're going to get, after projecting out the auxiliary variables, a tighter and tighter set, which will eventually become exactly the convex hull. And it becomes a convex hull for with n equal to the number of, for a degree equal to the number of binary variables. Is this clear? I didn't say one thing, but given that many of you are integer programmers, you probably know this. How do we project out all these variables? Fourier-Motzkin elimination. Can you imagine millions, you write down millions of constraints with a lot of auxiliary variables. Imagine applying Fourier-Motzkin to that sort of system. Can you tell me now, is this technique used in practice? But it's beautiful, right? So how many terms do we have for d equals 2? And let's suppose we have n binary variables. So we have n variables. Each of them can show up 0 times, once, or twice in the first set, twice, once, 0 times in the second set. I'm sorry?
Maybe we would like to just cut out one given point
Mm-hmm.
and not use all of the identity cuts.
Uh-huh. So you need to come up, so those are cuts, right? Once you, actually not even that, once you delete, once you project out all the auxiliary variables, you get a linear cut in the original space. But in order to get to a cut, and you want actually a cut that chops off the current point, you need to go through all this process. I think there have been attempts. I know of one PhD student who was working on this to precisely do some sort of separation like this in polynomial time, but I'm not sure how it's going. The given that you get for degree equals n facets of the convex hull, this, if you knew a way to use it, this would be powerful. More questions? Mm-hmm.
What is the complexity of Fourier-Motzkin? Because in the projection, I mean,
The worst case is exponential. I mean, you take all of these auxiliary variables, you take them with the positive sign, the negative sign, and you have a, so y12 appears in 10 inequalities with a positive sign and 9 inequalities with a negative sign. You have 90 extra inequalities to get rid of y12.